Hello, folks. So, today we'll be starting to look at Chapter 3 and the properties of light and how it directly applies to atoms and elements. But for today, we'll just be focusing largely on the properties of light and electromagnetic radiation. So, let's go ahead and get started. So, here, this chapter is called The Quantum Model of the Atom and Periodicity. So, we'll get right started. That while we may focus on light as a concept, really what we're really talking about is called electromagnetic radiation. That light is just, as a form of energy, is a form of electromagnetic radiation. And it can be thought of a moving wave of magnetic and electrical potential. That it can affect electronics, it can be affected by magnets, be affected by gravity, but it's not really considered matter per se, in that it does not have mass and does not take up space. Now, EM, we're going to abbreviate electromagnetic as EM. EM radiation can be absorbed by objects, it can be emitted by objects. Just lay out in the sun for any period of time, you'll feel your body heat up. That's you absorbing EM radiation of light. You've ever seen something glow in the dark, phosphorescence or fluorescence, where it glows after you shine some light on it for a while? It's emitting EM radiation. So now EM radiation can be refracted by passing through a prism, and basically these all things can. The prism is not the only thing that will refract light, but water will refract light, even air refracts light, and it does the same with all EM radiation. One of the things, though, is it can travel through a pure vacuum. Sound, not so much. Sound is essentially deals with the collision of particles together. In a vacuum where there are no particles, you're not going to hear any sound. It needs some sort of medium to pass through, but light can travel through a pure vacuum. Now, we always hear about the speed of light, this being the speed of light given the constant c, and this is 2.998 times 10 to the 8th meters per second, approximately 3 times 10 to the 8 meters a second, which is what, like 300 million meters in a second, essentially. But this is only the speed in pure vacuum. This is the essentially maximum top speed when nothing is affecting it. If it hits and passes through a medium, just like if you were to wade through heavy water, you'd be moving slower. So light will slow down in air, light will slow down in water, light will slow down as it's passing through a transparent solid like a prism. And that's what causes a lot of the neat effects we may see. You ever hear about in fishing, like in the book Hatchet, where you're like the boy Paul is trying to spearfish, and due to the refraction of light, he misses a lot at first because it takes him a while to realize that fish is actually a little bit closer to him than he thinks because of how the light appears. The water, that he thinks the fish is here, but the fish is actually there. And so that's because it's light is moving at a different speed in water, and it's being angled in a different way, and so you're getting a inaccurate reading, inaccurate perception. Distance, when we describe light or describe any type of electromagnetic radiation, there are several properties we will use to describe it. The first of which has to do with the fact that we see these guys as a wave that's constantly moving in one, just a repeating pattern, going up and down, back and forth. The first thing we're going to use to describe it is called the wavelength. It is represented by the Greek letter lambda, which looks like an upside down Y. This wavelength is simply the distance between two peaks or two troughs, or essentially what distance could be measured before the wave will start to repeat. Now, each color of light has its own unique wavelength. Some colors might be a combination of wavelengths, but for every unique color of light, there is going to be its own wavelength. So, red has its own wavelength, orange, yellow, green, all going to have a different wavelength. That's going to describe it. Now, another way we can describe these waves is with the amplitude. Now, we won't bother to do amplitude. That is more of a physics property, because amplitude in this case is the height of the wave, how big the wave is. A small wave on the beach, not very dangerous. A large wave, full of energy, able to knock you down, drag you back into the surf. Well, amplitude in this case is the intensity of the EM radiation. A very sunny day would be having very high amplitude waves. The very not very sunny day, very cloudy day, you might have very low amplitudes of light. So essentially, something that might absorb some of that light. If it doesn't absorb all of it, it essentially just makes the waves, shrinks them down. They're still the same wavelength, but they're shrunk down. So amplitude is independent of the wavelength. So as these waves are constantly moving forward, the image we see up there is just a stationary picture. But imagine this is a time lapse photograph of a wave passing through per second. You can see the shorter wavelength, the one with the smaller waves, has a lot more waves, a lot more repetition. The wave with the longer wavelength has a lot fewer waves that would pass through in that given time. So the other way to describe this EM radiation is with what we call the frequency, which is kind of like a curvy V, which is the Greek letter of nu. So the frequency is literally a rate, similar to a speed. When we talk about the velocity of a car, we're talking about typically in miles per hour, or meters per second, or kilometers per hour, or however you want to talk about it. You're talking about a distance applied over a time. Well, since instead of that, we are looking, this frequency is a repetition of how many waves pass through in a given time. Like you could talk about in the cafeteria, how many students enter the cafeteria in a given amount of time at the busy point. And you could look at it as students per minute. Now, because we know what we're constantly referring to as students, we could just, as a rate of per minute. Well, in this case, since it's always referring to the waves, how many waves have passed by, the unit is just per second, often given as inverse seconds, which is seconds to the negative first, or 1 over seconds, which is literally an inverse second. Now, you may have also heard this referred to as hertz. Hertz, 1 hertz is a 1 inverse second. So there's a straight 1-to-1 correlation. Where you might have seen hertz is if you're looking at, say, information about a speaker or about a microphone or something where they have audio quality. So we're looking at the frequency of how much audio fidelity, how many waves can it shoot out in a given second. The more waves, the more different sounds it can produce in a given time. So we're going to have a relationship with our frequency and our wavelength of our waves. Now, these two guys are interrelated. They're interrelated by the speed of light, such that if I take the wavelength and I multiply it by its frequency, it would always, no matter where we're at, always equal the speed of light. So, the longer the wavelength, the less the frequency, so the slower it repeats. The shorter the wavelength, the more repetitions you'll see. And that's what we can see in that image above. So they're directly related by the speed of light. So if we pay attention to our units, our wavelength needs to be in meters, and our frequency is in inverse seconds, and when we multiply them together, we get units of meters per second, which is the units of the speed of light. Now, this EM radiation covers a wide range on the spectrum. It's a very wide spectrum. We usually talk about light, but if you look on this little chart over here, light only covers the area between 750 nanometers and 400 nanometers. That's where we go from red all the way to violet on the Roy G. Biv scale. Everything above and below also EM radiation. So below red, we have infrared. Infrared. So below red. Below infrared, we have microwaves. So in wavelength scale, we're talking about millimeters or micrometers. Hundreds of micrometers or millimeters. Below that, we have radio waves. So these are getting into meters and hundreds of meters in distance. And we can eventually get to long radio waves. And some of these guys include television waves. So when we're shooting all of our information across the world, it's going to be in multi-meter, sometimes even kilometer size waves. Repeating waves. Now, on the other end, we have ultraviolet. Ultra, above, greater than. Ultraviolet. So these are in fractions of nanometers. We're talking about we're then above that we have X-rays. So getting really, really small. To single nanometers, or even, as I said, it's ultraviolet is sometimes 100 or less in the nanometers. X-rays are single nanometers or even less than that. And above even that is gamma rays. When we think about gamma rays are typically produced by the sun. That's where it's most likely going to be talked about being produced. But also, hear that as a trope in early superhero comics. These guys were bombarded with gamma rays, and that's how they got their superpowers. Unless you're talking about super cancer, that's probably all gamma radiation is going to give you, unfortunately. So, as we look at here, There's long wavelength, low frequency on the left ends of the scale, and high and short wavelength, high frequency. One thing we do know is that as we get to a higher frequency, a shorter wavelength, the energy associated with this radiation gets greater. So red light not as damaging as blue light or violet light. While you can't while it's not suggestible that you look at a red laser, a blue laser will definitely scar your retinas. Infrared radiation, not very damaging. Microwave, I mean, it could cook something, but it's not necessarily damaging. Radio waves and TV waves, not really damaging. Ultraviolet, that's what we talk about that gives us skin cancer, as well as X rays and gamma rays. They are high enough frequency that they can knock your DNA apart, and those damage to the DNA is what causes the cancer. So, it's the idea to keep in mind. Either way, regardless of what type of EM radiation, they all travel at the speed of light. They all have very similar properties. They all can travel in a vacuum. They all travel at the speed of light in a vacuum. They all can be refracted by various ways. So, when we shoot our TV all across the globe, it's also going out to outer space at the speed of light. The gamma rays shot from the sun travel to Earth at the speed of light. So, X-rays in the doctor's office zap you at the speed of light. So all these things are of similar properties. Now, light acts like a wave. However, there are several different times when it doesn't act like a wave, where it acts like a discrete amount of, like a particle, like something you could hold in your hand and you could measure, as opposed to a never-ending wave. So this is where light is unusual, or EM radiation is unusual. That this is something that scientists noticed, that if you take a monochromatic laser, which means a laser attuned to produce a single frequency, and they shine it on a piece of metal, if the light is of a certain frequency, the metal will emit electrons. It will shoot off electrons that could be detected by an electron detector. One that basically a current would flow because it's shooting electrons that can be picked up by the detector. And these are called photoelectrons. We call it photoelectrons because they are electrons emitted by light, photons. Now, if the frequency is low enough, no electrons. If it's high enough, there are electrons. If I were to increase the frequency above that threshold, so if I have, this is the magical line, anywhere below that line, no electrons, no electrons, no electrons, no electrons, we hit there, electrons. As we keep increasing the frequency, we do not get more electrons, but the electrons gain greater speeds. The electrons are given greater amounts of kinetic energy being described as mass, 1/2 mass times velocity squared. They have greater velocity being ejected. So, if we increase the amplitude of light, which is the intensity, we get more electrons. But if we're below the threshold, increasing the intensity still does not give you electrons. So the idea being you need the frequency above a certain wavelength. It doesn't matter how much light you have, as long as it's above the wavelength, you get some electrons. Now, everyone knows Albert Einstein for E equals mc squared, but he won his first Nobel Prize in physics for his explanation of this effect, of how to describe this. Explain this photoelectric effect is that light is acting like tiny packets of energy. We're calling those tiny packets of energy photons. If we're striking the metal and transferring this energy, and we have enough energy, photoelectrons can be ejected. Think of it like billiard balls. Like if you hit a billiard ball into the triangle at the very beginning, if you hit the cue ball, if you do not hit it with sufficient force, the balls are not going to move. But if you strike it with sufficient force, you can get a clean break where the balls spread everywhere. If it hits it weakly enough, it bounces off without really moving anything. But if we hit it with a sufficient force, it spreads everywhere. They all spread out. The idea is we have to have enough energy to essentially break up the inertia. Essentially, in that case, we have to break up the inertia and fight against friction to transfer that energy to eject a ball from our initial position. Well, the same thing. We have to have enough energy to eject a photon, to eject an electron. We have to knock it out by delivering enough energy. If you do it a bunch of times, it doesn't really matter if it doesn't have enough energy. But we need even one strike with enough energy, it's going to transfer energy and kick it out. Now, this light can therefore be both a wave and a stream of particles. However, it will only act as one or the other at a given time. This is known as the wave-particle duality of light. We only picture this as either a wave continuously or as a particle of light. When considering the particle nature of the photon, the energy delivered is a direct function of frequency. The energy is equal to Planck's constant times its frequency. Planck's constant is 6.626 times 10 to the negative 34th joule seconds. So it's accounting for all the things, and you will never need to memorize this. You will always be given Planck's constant. But essentially, if frequency is in inverse seconds and we're multiplying by a joule second, seconds will cancel out to leave us an energy in joules. This will often be a very, very small number. But considering the fact that we're talking about the energy of a single electron, it is expected to be a small number. Now, each metal has its own unique minimum energy threshold, which we can use to be described with the work function phi. And basically a simple math problem. If the light has enough energy for the electron to be ejected, so the difference between phi and the energy, any of that excess energy is converted into kinetic energy. So we can simplify the equation into kinetic energy is equal to h nu of the light minus phi. Of course, phi would always have to be given. So before moving on and actually trying some, we'll look at this. this particle duality a little bit more, and that one of the issues caused by this is black body radiation. A black body is an object that is capable of absorbing all the wavelengths of light. And that a black body is, once we absorb the radiation, it can we'll see something unusual. Usually a black body appears black at room temperature, but it doesn't have to be black by definition. But so lava, graphite, even stars and planets can be considered black bodies, even though planet Earth isn't really black. But so black body radiation is basically a way in which, when we heat up objects, when objects absorb enough thermal energy, they will begin to glow based on the temperature of the object. So lava, when it's hot, you get the oranges and the reds and but when it cools down, it goes to black, the obsidian. Steel, when you put it in the furnace, will glow first red and then orange and yellow before it starts to melt. This is directly dependent on their temperatures. Different colors of stars are based on the internal temperature of these stars. That red dwarfs, yellow suns, all that depends on the temperature, and that's because there's a direct correlation with the temperature and the wavelengths of light that would be emitted and their relative amplitudes. As we see at 3000 Kelvin up there, it's very weakly releasing light, largely in the infrared and highest intensity into the red. With the 4000 Kelvin, it starts to appear green, and that it is releasing energy in the red, but it's also releasing a lot more in the yellows and the greens, a little bit in the blue. As we shift, and it's slowly shifting further and further left as we up the temperature. So we're going to be blue. It is emitting a lot of yellows and greens, but also emitting quite a lot of blue. That this is what's causing the color change. So we can tell a lot about the temperature present based on how it glows. But okay, so the best thing we can do is just do some simple practice with this. So, first question, what is the frequency of 580 nanometer light, yellow light? What is the energy of that light? And if phi is equal to 1.52 times 10 to the negative 19th, what is the kinetic energy that would be shot off? We need a few equations. Lambda nu, E equals H nu, and then kinetic energy is equal to energy minus phi. And we also need a few constants, which I'm writing down now. Times 10 to the 8th meters per second, and Planck's constant 6.626 times 10 to the negative 34th joules seconds. Okay, with that in mind, let's look at the dot cam. Okay, with this in mind, first step is we want to solve for the frequency. So I have that up there. Rearranging this equation. So lambda. This is lambda we're given. Rearranging this equation, we have C divided by lambda equals nu, our frequency. Okay. Now we need to be very careful of the units. C is in units of 2.998 times 10 to the 8th meters per second. So 2.998 10 to the 8th meters over seconds. and I am dividing by my 580 nanometers. Now, meters and nanometers, as written, do not cancel out. Different factors of units cannot directly cancel. So, what must I do? I need to convert. Well, a nanometer is small and a meter is big. So, 1 meter, I know the 1 meter needs to go on bottom because I have meter on top, is what relationship? It's not 1,000, not 1,000,000, but 1,000,000,000. 10 to the ninth nanometers in 1 meter. So 10 to the third would be a millimeter. 10 to the sixth would be a micrometer. 10 to the ninth is a nanometer. So what I'm going to do, 2.998 times 10 to the 8, 998 times 10 caret 8 times 10 caret 9, and then I'm going to divide by 580. If I divide by 580, we get this number, which is in itself a big number. But that is, say 5.17. 5.17 times 10 to the 14th inverse seconds. That is a big number, but frequencies are often big, especially with visible light. Now, when I go to calculate the next step, which is converting this to energy. Energy equals H nu. Well, I just have to plug in my values. My first value is 6.626 times 10 to the negative 34th joule seconds over 1. And I'm multiplying by 5.17 times 10 to the 14th inverse seconds. 1 over second. Seconds and seconds will directly cancel. And so I just have to make sure I have all my units showing up right. 6.626 times 10 caret negative 34 times 5.17 times 10 to the 14th gives you 3.43 times 10 to the negative 19th joules. Please note, all visible colored light will be within that range. It should be very close to 10 to the negative 19th. If it is not, for visible light, you have done something horribly wrong. But all visible, red through blue, will be within that range. A little bit smaller, a little bit bigger. Now, so that is our second question. What is the energy? Then, last step, kinetic energy is equal to the energy minus my phi. So, which is 3.43 times 10 to the negative 19th minus 1.52 times 10 to the negative 19th. If this value was smaller than this value, we would have no kinetic energy. So just note that. But so set that up, 3.43 minus 1.52, all those times 10 to the negative 19th. Do that math. 1.91 times 10 to the negative 19th joules. 1.91. And that should be our final answer. There we go. So, as all in all, this part is a lot of repetition, Not a lot of difficulty. It doesn't have to be a lot of difficulty. But so, other factors of light. So, how does this really relate to atoms? All this is just pure light. Well, there's some neat things about light. For example, the white light we see when we look at light bulbs is actually a full spectrum of light. That this is the continuous spectrum that when they all add up, how our brain perceives this is the simple white light. But if we were to shine this through a prism, this is going to be separated into the uninterrupted rainbow called Roy G. Biv, which we call the continuous spectrum. That basically different wavelengths of light are caused to refract. They're caused to bend at different angles based on their frequency. And this bending causes them to essentially like separate out while they're both all in a line. It's like if cars are going down a track and line and they all hit a curve, but they're all going different speeds. Maybe if they all turn at the same point, the cars at faster speeds are going to zoom more out of the way than the cars moving slower. That would then essentially can make the turn a little bit more sharper. So it's like, how far do you zoom into the other lane in order to make that turn? It has to do with their frequency. And so they will all go and they all separate based on the relative frequencies. That some other things is that matter and energy are constantly interacting. They're absorbing. They can store that light and release it as excess energy. The basic idea of like fluorescence and phosphorescence is that objects are capable of certain objects are capable of absorbing this light, storing it for a period of time, and then once the energy source has been shut off, they will slowly release that light back out. And that's like glowing. You put the little like things on your ceiling as a kid, the little stars and not that glow green for a while after you turned off that light. They don't immediately go they don't immediately light up and turn off. They slowly trickle that light back off. That the colors of our fabrics, the colors in our dyes, all they absorb different frequencies of light. That what we actually see, the color we see, has to do with the absence of various colors that are produced. So we have the Roy G. Biv spectra. So if we draw a quick circle, I'm going to jump to the document cam. ROY, what is it? GBV. So ROY. So the appearance of red has to do with a fabric absorbing largely in the green. Chlorophyll is absorbing largely in the red wavelength. So my light blue shirt is absorbing a lot in the orange wavelength. Something that appears very purple, like this mug, would be absorbing largely the yellow wavelength. So various colors has to do with what wavelengths are being absorbed and what are being allowed to pass through or bounce off. So the stuff that bounces off, you may not get all of the colors back off again, but what we see is because red and green are not in equal proportions, one of them jumps out a little bit more intensely. Uh, Light can also be directly emitted just by introducing excess energy. So fireworks, when we burn, fireworks are just essentially the energetic release of energy stored in metals through combustion. We are essentially lighting up various metals along with some gunpowder, and as the gunpowder explodes, it ignites these metals and they release the excess energy from the burning as light. And by knowing what type of metal we have, we know what color we should get. That, like, coppers often produce blues and greens, that sodiums will produce yellows, and that magnesiums will produce whites. And so we can, by knowing which metals we have and mixing them into the firework, we can produce various colors of fireworks. And if you've always seen that magic campfire salt that you throw in the campfire after you're done cooking, and it causes the fire to change color, you're basically doing a firework without the gunpowder. You're throwing into the fire these heavy metals, and the fire will change color because the metals are burning off and producing this light. So, there's about one other thing, and that neon lights and others. So that we don't have to destructively excite metals. We can just electrically excite metals and produce colors. So in the case of a glass tube, if we take our simple cathode ray tube, which we talked about in chapter 2, and introduce a single gas, which just put one type of gas into this cathode ray tube, and then electrically excite it. So as the electricity flows through that tube, it causes the gas to light up and produce a single general color. Like if you talk about a true neon light are kind of a pale orange. If you've ever stared at the street lamps at nighttime, they produce a dull yellow light, which is from the sodium vapor. The heat of the electricity that produced by electricity causes the sodium to vaporize. So we have it in a gas form, and that is absorbing the energy and producing our yellow light. But if we have helium in the tube, it also produces a similar yellow. If we had pure hydrogen, it would produce red. Carbon dioxide would be a white light, and mercury vapors would be blue. Which is all well and good that we have different colors, but those colors are not a single frequency. If we were to take that light and diffract it through a prism, instead of giving the full spectrum of colors, we are going to get several distinct wavelengths that are dependent on this element. So in the case of hydrogen, down here we see hydrogen's red is not just pure red, it's like a bluish violet, a blue, like a greenish yellow, and some red. Mercury's blue is, we have two blues, quite a bit of yellow and greens, a little bit of orange, and maybe one red. That neon's orange has quite a bit of greenish yellows, quite a bit of oranges and reds. That each element has a unique emission spectrum. Each element has a unique line spectrum. We call this an emission spectrum because it is emitting light. Light is coming out of this. We call this a line spectrum because it's producing an individual line rather than a constant wave. It's not going to be a single rainbow, but actually unique lines. Alternatively, we can look at the opposite of the emission spectrum, which is the absorbance spectrum, which is that each element will absorb only specific wavelengths of light. And so we can look at the continuous spectrum as it passes through an element and see what has been subtracted. But the idea is that these emission spectrums are unique for each individual element. This was one of the ways scientists used to determine whether they have created or found a new element. They could electrically excite it, get the emission spectra, and then find out, does this contain a new spectra? Sometimes elements and compounds would contain a mixture. And so you'd get a whole mess of lines, some of which overlapping and whatnot, but they had books and books of every known element, and they could go, oh, we see these unique lines. These lines are not unique, though that's probably sulfur, but these lines are unique, and so whatever is not responsible for sulfur is this new element, which we can find. In fact, that is how we discovered helium. Helium was not discovered on Earth initially. It was discovered in the sun. We had created the line spectrum, the emission spectrum, and we wanted to probe the nature of the sun. We predicted there's hydrogen in the sun, and we looked at the sun and we go, yep, there's hydrogen, but oh, hey, there's a bunch of other lines we have not seen before. And that's how we found helium. And then knowing that this noble gas existed, we knew to look for it on Earth, and we eventually found it on Earth. It's a little bit harder because it's noble gas. It doesn't really react, but it is present. And so the reason it's called helium has to do with the Greek sun god Helios. And so we're naming helium in honor of and reference to him. So now how can we relate all this information about light and how light can come off atoms to our atomic structure? Well, the idea here is so remember we talked about Rutherford's model of the atom. We talked about how the electrons are in this cloud just swinging around the atom. It's kind of like a planetary model, maybe. But it wasn't really well understood. We just thought they're just floating around the nucleus. But if the radius were variable, then the energy emitted would be variable. Because to pull two attractive things apart takes a certain amount of energy. The distance will relate to the energy we need to extract them. So if the electron could be anywhere, the energy could be a wide range. However, we saw only specific frequencies in those line spectrums. And so we get a scientist by the name of Niels Bohr, who would create a model that would describe how these electron clouds work. The Bohr model proposed that the electrons essentially circle the nucleus at specific distances, we would call orbits. And each orbit has a discrete energy level. So we have a more or less constant orbit around the atom, and it's kind of like stairs, that each step is a unique stair. Each orbit is a unique stair, and to move up the next step takes a set distance. It's not this staircase has not been built slipshod where each stair is at a variable height and it's all crooked and bent. It's there's a unique distance between each stair step, and you could trust that, and it's very reliable. Well, looking at this, when we talk about this, the lowest closest energy level would be called the ground state, and any further or higher energy orbits called the excited states. So to move an electron up from one orbit to another would be to excite the electron. Now, the differences in energy related to the light absorbed or emitted by elements in the emission or absorbance spectra. So when we get those emission spectra or absorbance spectra, that's from the light, the electrons jumping from one step to another. So it absorbs this much light and only this much light because the electron only needs to jump this stair step. If you try to jump a stair step and a half, you're going to trip. So it only jumps one stair step, or it jumps two stair steps, but it doesn't jump any fractional stair steps. So we only get unique absorbances, but we only get single line absorbances for one unique frequency. Now, because we could go from step 1 to step 2, or step 1 to step 3, or step 2 to step 3, you get a wide variety of absorbances. The more possibilities, the more the lines. So the energy level gets closer together the farther you get from the nucleus. So, for example, the difference between the first and second step levels greater than the distance between the second and third, so on and so forth. So the electron can jump up 1, jump up 2, jump up 3, jump up 4, jump up 5, jump up 6, and keep going. Eventually it gets to a point where it's too far away from the nucleus. It's no longer being attracted to the nucleus, and we consider that distance infinity. So the electron has been fully removed and it's flung off. That's our photoelectrons. If it absorbs enough light, it just gets flung off. But any other proper frequencies, it absorbs it. And then once absorbed, it can emit that same wavelength right back out. But so when it fully gets absorbed and flings the electron out, we call this ionization. And the energy it takes to kick it all the way out is called the ionization energy. The energy to make an ion. But this last slide that we'll go through today, the Rydberg equation. While we will not use this equation, this is a very interesting aspect of science, that we can model these various energy levels in a hydrogen atom by using this equation. The equation simply states 1 over the wavelength of light produced is equal to a constant, that's for hydrogen, times 1 over n1 squared minus 1 over n2 squared. n1 and n2 are simply integer values, which means whole number values that directly relate to the ground state, or relate to the orbit. Integer 1 would be the ground state. Integer 2 would be the first excited state, second, third, fourth. Basically, how far away from the nucleus. And so 1 squared minus 2 squared, say 1 over 1 squared minus 1 over 2 squared times this constant would give us the wavelength of light that would be produced when the electron is moved from the first level to the second level. Then you could also look at, 1 over 1 squared minus 1 over 3 squared would be the energy to kick the electron to the second excited state. And you could use this to predict, and you can actually measure the distances between those frequencies, those wavelengths in the emission spectra. This equation will correctly predict all the energy levels for hydrogen. However, once we start adding in additional electrons, the math becomes impossibly complex and we can't really model this. And so we won't try to model this. And even though some books will ask you to do equations with this, I will not ask that of you. But why I think this is so interesting is that this equation was actually developed 30 years before the Bohr model. That they found these patterns, that these distances there relate to this simple mathematical function. This was created by I think a Swedish school teacher mathematician that he was doing some science and he figured out, well, we have these repeating patterns, that if I make this equation where this is the inverse of integers, I can get these distances that I can measure with a ruler. And so before we knew about these energy levels, we could predict it, at least for hydrogen. Now, with that in mind, that is where we'll stop. And from there, we will look at quantum models. But I think we've gone far enough, probably overly far. So, have a good day.